According to the National Electrical Code, the installed wiring harness described does not meet the definition of a multi-outlet assembly as defined in Article 100. A multi-outlet assembly is a single assembly that provides multiple outlets on a single back plate with multiple branch circuits, usually with simple one-screw wire termination. The wiring harness is a field-installed assembly with separate outlets that are not mounted on a common strap or backplate. When calculating the branch circuit load and understanding that the wiring harness is not a multi-outlet assembly, the calculation for the branch circuit load must adhere to the general rules for branch circuits found in Article 210.4 of the National Electrical Code. For a three-phase branch circuit, you can install up to 13 outlets on each phase. The triplex receptacle used does not fall under Article 210.4b multiwire branch circuits because it is not a multiwire branch circuit. A multiwire branch circuit requires at least two ungrounded conductors and a neutral conductor on the same branch circuit, with each phase supplying alternate outlets. In this case, the 5-wire harness includes 3 separate circuits, each with its own phase, neutral, and ground conductor. Let's delve further into these aspects to clarify the requirements and calculations involved. Firstly, understanding the definition of a multi-outlet assembly is crucial. As stated previously, it's a single assembly providing multiple outlets on a single back plate, often with simple wire termination. The key here is the single assembly aspect. The described wiring harness being field installed with separate outlets not on a common strap or back plate does not fit this definition. This distinction is vital because it affects how the branch circuit load is calculated. Secondly, regarding the calculation of branch circuit load, because the wiring harness is not considered a multi-outlet assembly, the general rules for branch circuits in Article 210.4 of the National Electrical Code must be applied. Article 210.4 provides the guidelines for branch circuit wiring. It specifies the permissible uses and the requirements for conductor sizing, overcurrent protection, and outlet devices. In a three-phase branch circuit, it is permissible to install up to 13 outlets on each phase. This number is derived from the load calculation based on the circuit's amperage rating and the assumption that each outlet serves a specific load. The specific load depends on what the receptacle is rated. Thirdly, it's important to understand why the triplex receptacle does not fall under Article 210.4b concerning multi-wire branch circuits. A multi-wire branch circuit, or MWBC, is a circuit that has two or more ungrounded conductors with a voltage between them, and a neutral conductor connected to the neutral or grounded conductor of a system. MWBCs serve multiple outlets or loads. They are wired in a way that the voltage between any two ungrounded conductors is higher than the voltage between any ungrounded conductor and the neutral. In the described scenario, the 5-wire harness includes 3 separate circuits, each with its own phase, neutral, and ground conductor. Because each circuit has its own dedicated neutral, it does not meet the definition of a multi-wire branch circuit as outlined in Article 210.4b. Multi-wire branch circuits share a common neutral conductor. Understanding these distinctions is essential for safe and compliant electrical installations. Now let's clarify some key terms and related concepts to give a more comprehensive understanding. Article 100 defines terms like multi-outlet assembly, branch circuit, and other critical terms used throughout the National Electrical Code. Consulting Article 100 for precise definitions is essential when interpreting and applying the code. A branch circuit, generally, is the circuit conductors between the final overcurrent device protecting the circuit and the outlet or outlets. It includes the wiring from the circuit breaker or fuse in the panel board to the points where electricity is used. Branch circuits are classified according to the maximum permitted ampere rating or setting of the overcurrent device. For example, a 15-amp branch circuit is protected by a 15-amp circuit breaker, a 20-amp branch circuit is protected by a 20-amp circuit breaker, and so on. Article 210 covers branch circuits. It provides requirements for the number and type of branch circuits required for various applications, the permissible loads on branch circuits, and the installation of branch circuit wiring and devices. The requirements ensure safety and prevent overloading of circuits. Article 210.4 specifically addresses multiwire branch circuits. It outlines the conditions under which multiwire branch circuits are permitted, the requirements for identifying the ungrounded conductors, and the limitations on the types of loads that can be served by multiwire branch circuits. The intention is to prevent hazards such as unbalanced loads and excessive neutral current. In the context of the workstation wiring harness, the question arises whether it qualifies as a multi-outlet assembly. Multi-outlet assemblies are commonly used in areas where numerous outlets are needed in a concentrated area, such as in retail displays, laboratories, or office settings. They provide a convenient way to supply power to multiple devices without running individual branch circuits to each outlet. However, they must be installed in accordance with the manufacturer's instructions and the requirements of the National Electrical Code. The key consideration here is whether the wiring harness is a factory-assembled unit or a field-installed assembly. If the wiring harness is a factory-assembled unit that meets the definition of a multi-outlet assembly, it would be subject to the requirements for multi-outlet assemblies in the National Electrical Code. However, if it is a field-installed assembly, as described, it would be subject to the general requirements for branch circuits. When calculating the branch circuit load for the wiring harness, it is necessary to determine the total load that will be connected to the outlets. This includes the loads of all the devices that will be plugged into the receptacles, such as computers, monitors, task lighting, and other electronic equipment. The load should be calculated in accordance with Article 220 of the National Electrical Code, which provides the rules for calculating branch circuit, feeder, and service loads. Article 220 requires that branch circuit loads be calculated based on the volt-ampere rating of the equipment or appliances connected to the circuit. For receptacles, the load is typically calculated at 180 volt amps per receptacle unless the actual load is known. If the actual load is known, it can be used instead of the 180 volt amps per receptacle allowance. In the case of the three-phase branch circuit, the load should be evenly distributed across the three phases to minimize neutral current. This can be achieved by connecting approximately equal loads to each phase. If the load is not evenly distributed, the neutral conductor may carry excessive current, which can overheat the conductor and create a fire hazard. Now let's consider the triplex receptacle in more detail. The fact that the triplex receptacle has three separate outlets that are terminated in a common connector does not change the requirements for branch circuit wiring. Each outlet is still considered a separate point of use, and the load must be calculated accordingly. The fact that the outlets are not physically mounted on a common strap is also not relevant. The key consideration is that each outlet is connected to a separate circuit, and the load on each circuit must be calculated separately. Article 210.4b addresses the use of multi-wire branch circuits. As mentioned, a multi-wire branch circuit is a circuit that consists of two or more ungrounded conductors that have a voltage between them, and a neutral conductor that is common to all of the ungrounded conductors. Multi-wire branch circuits are commonly used to serve multiple outlets or loads in residential, commercial, and industrial buildings. However, they must be installed in accordance with the requirements of the National Electrical Code. One of the key requirements for multi-wire branch circuits is that the neutral conductor must be sized to carry the maximum unbalanced load. The unbalanced load is the difference between the current on the most heavily loaded and grounded conductor and the current on the other ungrounded conductors. If the neutral conductor is not sized properly, it can overheat and create a fire hazard. In the case of the described workstation wiring harness, the 5-wire harness includes three separate circuits, each with its own phase, neutral, and ground conductor. Because each circuit has its own dedicated neutral conductor, it does not meet the definition of a multi-wire branch circuit. Therefore, the requirements of Article 210.4b do not apply. To summarize, when installing and wiring workstation wiring harnesses, it is important to understand the requirements of the National Electrical Code. The wiring harness should be installed in accordance with the manufacturer's instructions and the applicable codes and standards. The branch circuit load should be calculated accurately, and the wiring should be sized properly to carry the load. If multi-wire branch circuits are used, the neutral conductor must be sized to carry the maximum unbalanced load. By following these guidelines, you can ensure a safe and compliant electrical installation. The considerations discussed relate directly to electrical safety and code compliance. Ensuring that the wiring harness is not mistaken for a multi-outlet assembly is critical because the code provides different requirements for each. Multi-outlet assemblies have specific listing and labeling requirements that are not applicable to field-installed wiring harnesses. Incorrectly classifying the wiring harness could lead to improper installation and potential safety hazards. Calculating the branch circuit load correctly is essential to prevent overloading the circuit. Overloading a circuit can cause the circuit breaker to trip, which can disrupt the power supply to the workstation. It can also cause the wiring to overheat, which can create a fire hazard. Therefore, it is important to calculate the branch circuit load accurately and to ensure that the wiring is sized properly to carry the load. The use of multi-wire branch circuits can save materials and labor, but it also introduces additional safety considerations. If the neutral conductor is not sized properly, it can overheat and create a fire hazard. Therefore, it is important to understand the requirements for multi-wire branch circuits and to ensure that they are installed correctly. When working with electrical wiring, it is always important to follow safe work practices. This includes energizing the circuit before working on it, using properly insulated tools, and wearing appropriate personal protective equipment. It is also important to have a thorough understanding of the National Electrical Code and other applicable codes and standards. If you are not qualified to perform electrical work, you should hire a licensed electrician. A licensed electrician has the training and experience to perform electrical work safely and in accordance with the codes. The process of calculating branch circuit loads begins with identifying all the loads that will be connected to the circuit. This includes both fixed loads, such as lighting fixtures and appliances, and portable loads, such as computers and monitors. Once all the loads have been identified, their volt-ampere ratings should be determined. The volt-ampere rating is the product of the voltage and the current that the load draws. It is typically listed on the equipment nameplate. For receptacles, the load is typically calculated at 180 volt-amps per receptacle, unless the actual load is known. If the actual load is known, it can be used instead of the 180 volt-amps per receptacle allowance. After the volt-ampere ratings of all the loads have been determined, they should be added together to determine the total branch circuit load. The total branch circuit load should not exceed the ampacity of the branch circuit conductors. The ampacity of a conductor is the maximum current that it can carry safely without overheating. The ampacity of a conductor depends on its size, insulation type, and installation conditions. The ampacity of conductors is listed in the National Electrical Code in Table 310.15. If the total branch circuit load exceeds the ampacity of the branch circuit conductors, the conductors must be replaced with larger conductors that have a higher ampacity. Alternatively, the number of loads in the circuit can be reduced. In the case of a three-phase branch circuit, the load should be evenly distributed across the three phases to minimize neutral current. This can be achieved by connecting approximately equal loads to each phase. If the load is not evenly distributed, the neutral conductor may carry excessive current, which can overheat the conductor and create a fire hazard. To ensure that the load is evenly distributed, a load balancing calculation should be performed. This calculation involves determining the current on each phase and adjusting the loads as necessary to balance the current. The neutral current can be calculated using the following formula. The neutral current is equal to the square root of the sum of the squares of the phase currents. If the neutral current exceeds the ampacity of the neutral conductor must be replaced with a larger conductor that has a higher ampacity. Alternatively, the load can be rebalanced to reduce the neutral current. In addition to calculating the branch circuit load, it is also important to select the correct overcurrent protection device. The overcurrent protection device is typically a circuit breaker or fuse. The overcurrent protection device is designed to protect the circuit from overloads and short circuits. It does this by interrupting the flow of current when the current exceeds a predetermined value. The overcurrent protection device should be selected to have an ampacity that is equal to or less than the ampacity of the branch circuit conductors. If the overcurrent protection device has an ampacity that is greater than the ampacity of the branch circuit conductors, the conductors may be damaged by an overload or short circuit. The National Electrical Code provides detailed requirements for the selection and installation of overcurrent protection devices. When installing receptacles, it is important to follow the manufacturer's instructions and the requirements of the National Electrical Code. Receptacles should be installed in accessible locations and should be securely mounted. The wiring connections to the receptacle should be made using approved methods and materials. The receptacles should be grounded properly to protect against electric shock. In the case of the workstation wiring harness, the receptacles are mounted in the top of the raceway, facing up behind a flip-up door at desktop height. This installation method may present some challenges with respect to accessibility and grounding. It is important to ensure that the receptacles are accessible for maintenance and repair. It is also important to ensure that the receptacles are grounded properly to protect against electric shock. The National Electrical Code provides specific requirements for the grounding of receptacles. These requirements are designed to ensure that the receptacles are effectively grounded and that there is a low impedance path for fault current to flow back to the source. The grounding conductor should be sized in accordance with Table 250.122 of the National Electrical Code. The grounding conductor should be connected to the grounding electrode system at the service equipment. In addition to the requirements for branch circuits and overcurrent protection, the National Electrical Code also contains requirements for the installation of equipment. These requirements are designed to ensure that equipment is installed safely and in accordance with the manufacturer's instructions. The National Electrical Code also contains requirements for the maintenance of electrical systems. These requirements are designed to ensure that electrical systems are maintained in a safe and reliable condition. The maintenance of electrical systems should be performed by qualified personnel. The maintenance should include periodic inspections, testing, and repairs. By following the requirements of the National Electrical Code, you can help to ensure a safe and reliable electrical system. Remember to consult the latest edition of the National Electrical Code and to consult with a qualified electrician if you have any questions. The National Electrical Code is a complex document, and it is important to have a thorough understanding of its requirements before performing any electrical work. Now let's discuss some practical examples. Consider a workstation with the following equipment: a computer with a power supply rated at 300 volt amps, a monitor rated at 100 volt amps, a task light rated at 50 volt amps, and a phone charger rated at 10 volt amps. The total load is 300 plus 100 plus 50 plus 10, which equals 460 volt amps. If the workstation is connected to a 120 volt branch circuit, the current draw would be 460 volt amps divided by 120 volts, which is approximately 3.83 amps. This is well within the capacity of a typical 15 amp or 20 amp branch circuit. However, if multiple workstations are connected to the same branch circuit, the total load could exceed the capacity of the circuit. For example, if 5 workstations with the same equipment are connected to a 20 amp branch circuit, the total load would be 5 times 460 volt amps, which is 2300 volt amps. The current draw would be 2300 volt amps divided by 120 volts, which is approximately 19.17 amps. This is close to the capacity of the 20 amp branch circuit. If any additional loads are connected to the circuit, it could easily become overloaded. To prevent overloading the circuit, it may be necessary to connect the workstations to separate branch circuits or to use a higher capacity branch circuit. Another example: consider a workstation with a high-powered computer that has a power supply rated at 600 volt amps, a large monitor rated at 200 volt amps, a printer rated at 100 volt amps, and a personal fan rated at 50 volt amps. The total load is 600 plus 200 plus 100 plus 50, which equals 950 volt amps. If the workstation is connected to a 120 volt branch circuit, the current draw would be 950 volt amps divided by 120 volts, which is approximately 7.92 amps. This is still within the capacity of a typical 15 amp or 20 amp branch circuit. However, the higher power consumption of this workstation should be taken into account when planning the electrical system. It may be necessary to use a dedicated branch circuit for this workstation or to use a high-capacity branch circuit to accommodate the increased load. In the case of multi-wire branch circuits, it is important to ensure that the neutral conductor is sized to carry the maximum unbalanced load. For example, consider a multi-wire branch circuit that serves three 120-volt loads. Load 1 draws 10 amps, load 2 draws 8 amps, and load 3 draws 6 amps. The current on the neutral conductor would be the square root of the sum of the squares of the phase currents. In this case, the current on the neutral conductor would be the square root of 10 squared plus 8 squared plus 6 squared, which is approximately 14.14 amps. The neutral conductor must be sized to carry at least 14.14 amps. If the neutral conductor is not sized properly, it can overheat and create a fire hazard. The examples highlight the importance of accurate load calculations and proper wiring practices. By following the requirements of the National Electrical Code and consulting with a qualified electrician, you can help to ensure a safe and reliable electrical system. Always prioritize safety when working with electricity. Electrical work can be dangerous if not performed properly. If you are not qualified to perform electrical work, you should hire a licensed electrician. Now let's look at some common mistakes to avoid when working with workstation wiring harnesses. Firstly, failing to properly identify the type of wiring harness. As discussed earlier, it is important to distinguish between a multi-outlet assembly and a field-installed wiring harness. Incorrectly identifying the wiring harness can lead to improper installation and code violations. Secondly, neglecting to calculate the branch circuit load accurately. Overloading a branch circuit is a common cause of electrical problems. It can cause the circuit breaker to trip, which can disrupt the power supply. It can also cause the wiring to overheat, which can create a fire hazard. Always calculate the branch circuit load carefully and ensure that the wiring is sized properly to carry the load. Thirdly, improper grounding of receptacles. Grounding is an essential safety measure that protects against electric shock. Receptacles must be grounded properly to ensure that there is a low impedance path for fault current to flow back to the source. Failure to ground receptacles properly can create a serious safety hazard. Fourthly, using undersized conductors. Conductors must be sized properly to carry the load. Using undersized conductors can cause them to overheat, which can create a fire hazard. The ampacity of conductors is listed in the National Electrical Code in Table 310.15. Always consult this table to ensure that the conductors are sized properly. Fifthly, neglecting to use proper wiring methods. The National Electrical Code specifies the acceptable wiring methods for various applications. It is important to use the correct wiring method for the specific application to ensure a safe and reliable installation. Sixthly, failing to follow the manufacturer's instructions. Equipment should be installed in accordance with the manufacturer's instructions. The manufacturer's instructions provide important information about the proper installation and operation of the equipment. Seventhly, not having the work inspected by a qualified inspector. Electrical work should be inspected by a qualified inspector to ensure that it complies with the National Electrical Code and other applicable codes and standards. An inspection can help to identify potential problems and ensure that the work is performed safely and correctly. Eighthly, not using a licensed electrician. Electrical work can be dangerous if not performed properly. If you are not qualified to perform electrical work, you should hire a licensed electrician. A licensed electrician has the training and experience to perform electrical work safely and in accordance with the codes. Ninthly, modifying equipment without approval. Equipment should not be modified without the approval of a qualified engineer or inspector. Modifying equipment can void the warranty and can create a safety hazard. Tenthly, ignoring warning signs. Warning signs are placed to alert people to potential hazards. Always heed warning signs and take appropriate precautions. By avoiding these common mistakes, you can help to ensure a safe and reliable electrical system. Always prioritize safety when working with electricity. Remember to consult the latest edition of the National Electrical Code and to consult with a qualified electrician if you have any questions.